Hi everyone, this is July 4th weekend, so we thought we thought we'd bring you something a little different, but nonetheless fascinating. I know I'm looking forward to heading over to my town pool tomorrow for fireworks. I hope you all can have a great weekend. So without further ado, we have here a situation which I think many of you, being the in-crowd largely, have dealt with. We do cutting-edge projects, and SEER, of course, is useful for estimating a lot of those projects. However, when they're still in the lab, there's still a gleam in their inventor's eyes, overhead costs maybe, internal R&D. You don't yet necessarily know how long they're going to take to reach fruition, to reach a manufacturability. And at that point, many parametric methods tend to be unsuited, unuseful, because they're still too far into the lab. And that's what this whole presentation and discussion is intended to help you address. We're here to help you not just with things we can estimate, but with things we know we can't yet. And while I go through all this with you, I'd love it if you came back with comments to us, and I can even share them with the group about how you estimate early in the lab technologies. I think most of us recognize some of the projects on this screen, which a good number of them have reached fruition, although after a long and painful gestation. The Osprey, the F-22, the Littoral Combat Ship, a few of them have been canceled, and that includes, of course, the Future Imagery Architecture, which was a huge blow-up from 2 years ago. I'm sorry, some of you may have worked on it, and I apologize for bringing that one up. There's I think that's the Striker, which the Marines wanted to let float here, floating off San Diego in its demonstration stage, but canceled also. And then, of course, the Xbox, the Operation X500, my childhood toy, which never quite reached its operational stage. This is not a new situation, going back here to New York Times 2005. It's been a constant situation for many years. I just read this morning, actually, about how defense acquisitions officials want to return to a Skunkworks era to try to push through things better, faster, cheaper. Best of luck with that. We go through the whole roll call. This was in 2005 again, of all the items that ran into serious trouble, and many of which were actually canceled. So we're not just losing money on these. If you look at the totals, we're actually basically investing the cost of entire weapon systems in lost projects. That's at a big level. If you turn over to the commercial world, you find the challenges are no less severe. Those were past defense projects, but we look at the roster of things that we want to develop in the commercial world: cellulosic ethanol, maybe CO2 sequestration systems, prosthetics, improved prosthetics, space elevators. All these are huge, grand challenge projects that are still in the lab, which people have no real idea what their costs will be. Of course, it's not just technologies that are immature. We can go back to the GAO reports and all the messed up government projects, and we know that there's more than just bad technologies. It's an interaction between customer and client, and the requirements may grow. They may be too stringent. Complexities, unresolved complexities, and then, of course, what we're focused on here, new technologies. So by all means, this is not a problem, overruns, limited to simply new technologies. And I'm going to just start the presentation by recognizing that, although we'll remain focused on the light blue. The challenges will grow as we stay on the cutting edge, and in fact, to remain competitive, we must remain on the cutting edge. This is a projection of some of the technologies. This is just a cutoff of a larger infographic. some of the technologies leading out that we'll be concerned with, and we still are facing issues with. A lot of these technologies, you can look at them. We understand a good amount of them already. Software agents, machine translation already well underway, speech recognition, but fuel cells sort of underway. But some of these we really don't yet know well. For example, smart drugs, picoprojectors, haptics, they're all in their incipient stages where we really don't understand their costs very well. Smart toys, I'm giving my kids just wooden toys, so we don't have to be worried about that in my house. Now, we have to differentiate very carefully between what's complicated and what's really just wondrous. So the tangled ball, simple stuff, I believe the C-17 was a great example of a systems engineering problem where a lot of different things needed to be integrated onto one aircraft, and it was just a hard problem. It wasn't as much a ball of weird stuff. However, the cutting-edge technology is a different story entirely. It's way in the lab. It's not that it's complex. It's that it may be complex, but it's also at its core something magical. Who was the science fiction author? A quiz for those of you out there, you can respond with the answer, who said that any technology that's sufficiently advanced is indistinguishable from magic. That's what we're talking about. Those magic projects are the ones which break the envelope. Many of you are no doubt familiar with the TRL Scale. For those of you who are not, we'll spend a little time on this. The Technology Readiness Level scale, developed at NASA initially, describes where a technology stands in terms of its ability to be fielded or put into production. TRL 1, 2, 3 are regarded as low TRL, and those items still require evolution and R&D in order to move them up the scale into demonstration, development first, demonstration, until finally when you reach the black, TRL 7, you can start considering their being placed into fieldable systems. There's a very nice calculator for determining TRL. It's offered by the Defense Acquisition University. If you just search for TRL Calculator, you'll come up with this calculator. And it breaks out the TRL levels into a significant number of specific considerations, a checklist for each TRL level from TRL 1 all the way through 9. I just show here the lowest and the highest level to give you a sense of what those considerations are. Physical laws and assumptions used in new technologies defined. Paper studies confirm basic principles. I think they mean back of napkin. If you go all the way to TRL 9, you're dealing with the workaday details of putting a system out, training plan, supportability plan. Obviously, there's no technical leap involved in 9, but in TRL 1, research hypothesis formulated, you're talking way, way, way deep in the test tube there. So this is also a link for those of you who'd like the straight link. But again, you search for TRL Calculator, you'll find that. The core of our presentation today is how do you estimate this stuff? Well, we've dreamed up, or rather, we've utilized and had experience in various guises with these 5 methods. And for each of the 5 methods, I've laid out the considerations in terms of the strengths, potential weaknesses. Expert opinion is a common one. It's kind of like a menu, I think. The way you build a menu in a restaurant is you put the stuff that you want people to choose at the top and the bottom. But they're all potentially relevant. Expert opinion via multidimensional Delphi. I'll get into all of these later. That's why I've numbered them. Model derived from past experience. This is the blank sheet one, but I provide some considerations that might go into building such a model. financial forensics, taken largely from the business intelligence realm. How long is something going to take to develop? It depends partially on how much you and your competitors are putting into R&D for that. Continuing cost of research, which is a gross measure of, or brute force rather, measure of determining future costs, but it may ultimately be the one that's most commonly used. And patent evolution, something I think venture capital firms are more likely to engage in. But as we cross-fertilize all their industries, we find that us developers are relying on other tools from venture capital, from business intelligence. They're all appropriate now, no matter what industry you're in. I would say that once you determine the method that's suitable for you, hopefully you'll have more than one, and you'll integrate them into a combined estimate, because you're dealing with such a high level of risk, needless to say, that you'll want to have more than one estimate. Oftentimes our parametric estimates are used alongside other estimates, and we encourage that. It reduces risk and results in a more defensible estimate. First approach, expert opinion via multidimensional Delphi. So it's a mouthful to say that, but it's actually quite simple. The idea is that you recruit multiple experts and you ask their opinions. That's the basic idea. But to reinforce that idea, you actually integrate a Delphi process. For those of you who don't know how Delphi works, it's a iterative process where you ask experts' opinions of a topic, and then you expose them to each other's opinions, and they're forced, if necessary, to revise their opinions until you achieve stable responses from each expert, and then you can integrate those. We have a tool which can aid in that process, estimate by comparison. The advantage of using tools such as ours is that when you're getting experts' opinions of a project and how long it's going to take, or technology and how long it's going to take to develop, you can select past work that's been done in the organization and let the experts, each of them, work through the process of estimating a new project using a tool like this. So let's say that you have experts 1, 2, and 3, and you're asking them how long the new project is going to take, the new technology is going to take to develop. You can say to expert 1, 2, or 3, we've done 4 projects in the past, the WYSIWYG, the ZZYZX, the Nevada project, and the Gizmo. How much time or how much work is this new project going to take relative to those past projects? And they can each go through this process, come up with a figure of merit, and then you can compare all their estimates. That could be a very, very robust way of determining the new project's time or cost to develop using this method. For those of you not familiar with estimate by comparison, it's similar to AHP. It's more accurate, actually, and it's been released as a SEER tool for many years now. Very useful for a project like this. I'm not going in order, that's why I've numbered all these things. Approach 5, patent devolution, looks at how an industry is doing. So if you're, for example, developing a new material, you can actually visualize the landscape of patents issued, not just for that material or similar, but across a much wider area. These are 3 of the most common. There are other means of patent visualization. So you can actually look at them as a topological view here, or a tree map here, or a network diagram here, and get a sense when you're asked to look at a new technology and how long it will take to develop. You can actually say, well, patents have been concentrating here, or patents are not, and we can't, for example, buy a portfolio of patents, and this we're going to have to develop it in-house. Or there are a bunch that are similar to this, So I can see that technology, even though the patents are, of course, proprietary, there is a general sense, there is a general overflow of knowledge as a field evolves, and seeing patents moving in a certain direction, potentially the direction you'll need to develop in, is going to be helpful for you. It also is useful if you want to see if the area you're working in is too crowded. Like I said, you could either purchase that portfolio, you could just decide not to enter an industry because it's going to be filled with a lot of IP that will be defended when you get there. So this is a great entry-exit decision as well to make, not just costing technologies, but deciding whether you want to get in there or not. Approach 4 is continuing cost of research. It's very, very, very straightforward. How much are you investing in something, and how many years do you develop? How many years have you been doing it, and can you extrapolate from that? The shades here are just simply different cost components. I haven't spelled them out. I just put them in just to represent the idea that you might have different components to your work. It could be that you have lab costs, overhead costs, management, or whatnot, and they ought to be broken out if necessary. And you just estimate the cost of developing over time until that lab has produced something that can exit the lab. Some questions to ask in estimating lab cost over time. Again, we have the dimension from TRL 3 on, or from TRL 1 on. That X dimension, how many years to TRL 7, can be answered by estimating, I'm just reading from the chart here, the number of years required for previous evolutions of the target technology. If it takes maybe 3-4 years for a low TRL technology to exit, then it may take 3-4 years for that next TRL technology to exit. I know that some corporate labs choose not to have very, very low TRL technologies in the lab. They choose to take them on once they've reached a certain level, and then they can more readily progress them to a higher level. So the question often can be answered, how long does the technology take to evolve? Because you'll only enter that technology development when you're at that point. And then, of course, how much is spent in the R&D for that. That would be the y-axis. The danger, of course, in estimating a technology's development is that you can't look forward perfectly. That TRL, that technology progression curve could look, just like, for those of you who tried to predict the price of your stock holdings, you know that the past is no representation of the future. So if you're here at this inflection point, you may just think it's going to go up forever, but as we learned in 2010, and so that inflection point may actually be an inflection point and not be a path forward, but a path in a different direction, or who knows, really. So when trying to predict the path of future technologies, you're faced with this conundrum. You have to, of course, be wary of that. Approach 2, developing a model, would be a wonderful way to estimate development, but it's a difficult one because it requires answering many questions, which can vary with the project. However, I mention it here because it is such a great idea if you can do it. You have to look at the success rate of past outcomes, years of research, how much spent, so that's the cost of technology over time, staff, etc. This list, in fact, the presentation is available to you afterwards for asking. So you need just to ask us for this, and we'll provide you with not only with the presentation as you see it, but some additional pages that talk about some additional thoughts on this topic. Approach 3, the financial forensics method, the business intelligence method, competitive intelligence, as some people call it. How much is it costing firms to get through this? how much does it cost in your firm? The competitive intelligence, business intelligence applies, looking inwardly in addition to outwardly. Once you have all the methods available, I have 5 shown here, but you may only have 2, then you combine them. And the method of combination may not necessarily be strictly putting them together and taking an average among them all or a median, but it may actually require some fudging depending on the relevance of each method, the data available for each method, and other considerations. And as long as they're given defense, I would venture to say that combining them with fudging is going to be defensible. Experience curves are common for forecasting. However, the experience curve is not as much for very, very low TRL technologies, but more for manufacturing readiness. And I have put them in here, although I haven't mentioned them as one of the methods you'd use, because these would come in at a TRL, I think, 7 or so level, not beforehand. But nonetheless, they are helpful later on. This being a Gallup presentation, I'd be remiss if I didn't mention some of the things that we do have available for you to estimate relatively low TRL technologies. In this snap of SEER, I show some of the things you can do to estimate, for example, a notional spacecraft here. We have the EOS model, to be clear, model, electro-optical sensors model for estimating advanced sensors on that spacecraft, and we constantly update that to keep it abreast of the state of art. The stable technologies, so even the point I'm making here before I get involved in all the other things on the screen here, the point I'm making is even an advanced system is a sum of many subsystems, some of which, the mechanical elements, the structural elements, many portions of that system are going to be very well understood, and you can still use conventional estimating, such as SEER provides, to estimate the balance of a system. There may be certain specific items on here that need advanced estimates. So EOS model, SEER EOS model estimates the sensor. Stable technologies estimated on here can be estimated using SEER. The far out model can estimate the entire spacecraft for a reference point. And advanced technologies alone, maybe that little box on there, would have to be treated separately using methods such as in this presentation. So the idea of an entire system that's not estimatable, it may be something less than the truth. It could be just portions of it. We also did a lot of work a few years back for AFRL under an SBIR contract with some of the models that I and my team use kind of here around the periphery. So for pretty advanced estimating stuff where there isn't necessarily good data or the methods there aren't appropriate, you can also give us a call. We'd be happy to help you out on that if we could or if we can. That's the presentation. I'm leaving this with a slide here. I'll give you a second. This is a little quiz for you guys or gals. I'd like you to try to figure out who of each of these people are. And I'm going to just give you a few seconds, and the answers will come up on the screen. Okay. Ready? 5, 4, 3, 2, 1. There you go. Famous inventors from yesteryear and just a few years back. And that line will probably continue. All right, questions?